Hello, my name is Henriette. I'm a PhD student in astrophysics at Charles University in Prague, and the following is a re-recording of a talk I gave at Astronomy on Taps at the Tequila Tales in Prague. Astronomy on Taps is a monthly science outreach event where my colleagues and me explain astronomy. Now, this is Prague, minus the buildings and minus the mountains. And at the moment, the sky is still a little bright to really see a lot of stars. So let's just turn forward the time a little bit. Now we see some stars. And if you are outside stargazing like that, you will of course ask yourself, okay, how do I orient myself? Where is north, east, west, and south? And to do that, you want to look for a constellation that consists of 7 very bright stars up here. This is what we call the Big Dipper. The Big Dipper is part of a larger constellation called the Big Bear. And if you take those 2 stars here and you go along the line between those 2 stars, and at the real sky, you would have to make 5 jumps along here to get to this star, the North Polar Star. Now, it doesn't work as well on this artificial sky, which is because we have the sky projected onto one plane. But this North Polar Star is part of a smaller constellation called the Small Dipper, which goes along here. Unfortunately, consists out of rather faint stars, so you can't find it easily on its own. But let me just turn on the constellation lines for you. So now you see very clearly this constellation here. And if you go towards this north, if you look towards this North Polar Star, you will always end up north. So we have the center of the sky somewhere here. We go through the North Polar Star and we would end up somewhere here. So north must be in this direction. And as we are on the sky, east is to the left of north. That's because we are looking upwards. West is to the right and south in the opposite direction. So let me just turn on the cardinal points for you. And you see here is north, here is east, west is down here, and south over here. Now, seeing all of those stars on the sky, you might ask yourself, well, how exactly did all of these stars form and where? And to answer that, let me just go down to the southwest here. And what we see here is another very famous constellation. This is Orion the Hunter. And below Orion are his 2 hunting dogs, here half behind the horizon, with the very bright and well-known star Sirius. And if we look to the left of this dog, we find the constellation Puppis here, looking up from beyond the horizon. And if we zoom in here, you will see that there are more and more stars. And on a clear sky, you can see those stars. And I want to now focus in on to these 2 stars here. And with a naked eye, you would just see that there are these 2 stars. But if you look through a telescope, you will actually see that there is here this grouping of stars. This grouping of stars is what we call a stellar cluster, which is in this case called the butterfly cluster. And you can see kind of the shape of a butterfly. Now, stars usually form in these stellar clusters. So if we want to understand how stars form, we must understand how stellar clusters form. And for that, let's just go a little bit over here inside of this Puppis constellation. And we see here, this is the Skull and Crossbone Nebula. Now, again, with the naked eye, we actually don't see too much of it, but luckily we have telescopes. This is what the Skull and Crossbone Nebula looks like if you look at it through the Very Large Telescope in Chile. The Very Large Telescope is actually not only one telescope, it is 4 telescopes like this in the desert in Chile, and they can be used either together or individually. And they give us pictures of this. So this Skull and Crossbone Nebula is a star-forming region. You see here the bright stars that formed. and the gas around it, which is the remains of the gas cloud, is formed out of. And stars in general form out of these giant molecular clouds floating in space. Now, we get actually even more detail of this if we look just in nearby regions. So if we zoom out here and we go back to the Orion constellation that we talked about, you might already see that this here is the sword hanging from Orion's belt. And if we zoom in here, this is probably the most studied star-forming region we have nearby. And if we look through at this with a telescope, in this case, this is a composite image taken by multiple telescopes. And here you see star formation in progress. So molecular clouds, if they start forming stars, they form these filaments, here seen in green in the foreground. Along these filaments, we have these individual stellar clusters forming. Here in the end, these clusters are already done forming and they have expelled all of the remaining gas through stellar winds and also supernova explosions, while along these filaments here, these clusters are still forming and are still embedded in gas. These molecular gas clouds here, they are usually chemically homogeneous, which means that we have the same chemical composition here as we have here, the same amount of sodium, oxygen, and so on. And it means that, of course, if we form these stars at all of these different regions, the stars must all have the same chemical composition. And for open clusters like the ones I showed you so far, this is true. However, those are not the only clusters we have. If we look at our Milky Way, so here we have the Milky Way, the center with a black hole in it, the sun somewhere halfway at the disk, 8 kiloparsecs away from the center. And if we look at it from the side, we have here this disk. This disk is where star formation happens. That's where those molecular gas clouds are, and that's where the open clusters we saw happen. However, in the halo around the Milky Way, we do actually get a lot of very old clusters. These are called the globular clusters. They are usually about 12 gigayears old, and they have a peculiarity. But before I go towards that, I should maybe show you where you can find a globular cluster on our sky. So let's go back to our sky. Let's zoom out a little bit. And to find possibly the most well-known, or one of the more well-known globular clusters, we must go a little bit forward in time towards 2 hours after midnight. And if we look in the southeast here, we see part of Scorpius. And if we turn on actually the deep sky objects here, here we have marked a cluster which is called the Crab globular cluster. Now, this cluster can be seen with the naked eye, but it's very faint. And you definitely can't tell with the naked eye that this is actually a star cluster containing all of these many stars. Let me just turn off the deep sky objects. So here, this faint little dot, this is the Crab globular cluster, also called Messier 4. And it's called Messier 4 because Messier in the 18th century was the first one who looked at it with its telescope and actually could resolve individual stars. So if we look at it through our telescope, this is what this cluster looks like. This picture was taken using the Hubble Space Telescope. And looking at this picture, we can immediately tell that this is an older cluster. How can we tell? Well, after stars are born from their initial gas cloud, they will start fusing hydrogen into helium. Doing so, they will gain some energy, which is then emitted as light. And these small white stars in the background do exactly that. The big red and blue stars in the foreground, they have depleted all the hydrogen in their core. So what they are doing now is that they fuse helium into heavier elements like beryllium, carbon, and so on. And It takes a while for these stars to get to that stage, so we can tell that the cluster must have been around for long enough. Now, I told you these clusters have a peculiarity. When we talked about open clusters, I mentioned that open clusters will have stars that are all chemically homogeneous because they formed out of a gas cloud that is chemically homogeneous. However, if we actually take the spectra of these stars and deduce the chemical composition inside of these stars of this globular cluster, this is the plot we find. So what do we have here? We have here on the left a plot that shows the oxygen content compared to the amount of iron in the individual stars of that cluster. And then on the y-axis, we have the sodium content over iron. We always use iron as a point of comparison because the iron content in the individual stars of a cluster stays relatively constant. If we look inside of this plot, we see there are big filled symbols and small empty symbols. That's simply because this is a composition from two different surveys. And what we see also is that we can divide the stars in this cluster into two groups. So we have a oxygen poor sodium rich group on the top left here, and we have an oxygen rich sodium poor group on the bottom right. If we look at the same stars and we look at their magnesium and aluminum content, we don't see that much of a difference. It's only a slight tendency here. But this is actually a pattern that repeats in many globular clusters. Globular clusters, or the stars within globular clusters, are not chemically homogeneous. So how can that be? Well, in astronomy, we still think that these clusters formed out of chemically homogeneous gas clouds. And what the most popular hypothesis for this question is that we take a chemically homogeneous gas cloud and we form some stars out of it. Then we pollute said gas cloud and form more stars out of this gas cloud that now has a different chemical composition. However, the question then becomes, well, how do I actually pollute a giant molecular gas cloud floating in space? And these clusters are massive. They are easily a couple million solar masses. There have been a number of suggestions over the years. One of the most popular is probably the AGB scenario. So we have these asymptotic giant branch stars. This is one kind of giant branch that exists. And they are distinct because they are very evolved stars and they have strong stellar winds. So of all the material they processed over time, they can expel a lot of it. Now, the problem with the AGB stars is that the stars first have to evolve to that stage. And that means that at that point, when these stars actually can expel material into the cluster has already gotten rid of the surrounding gas cloud. So in this scenario, we have to form a new gas cloud out of the ejecta of these stars and maybe some accreted star gas inside of the cluster to form new stars inside of it. The second hypothesis is rapidly rotating stars. Now, this is an outline of a star called Archena. Archena is very famous because of its oval shape. And this is a plot from measurements. You cannot simply make a photograph and see the shape of the star because you are literally photographing inside of a light source. And if you are looking directly inside of a light source, it's not that easy to see the shape. But we have measured this. And this is the result. And Archena has this oval shape because it's rotating very rapidly around this axis here. What happens if we have rapidly spinning stars are two things. For one, as I told you, stars fuse hydrogen into helium inside of their core, and then they fuse helium into higher elements. However, the outer layers of the star don't experience any nuclear fusion. So if I have a massive star, on the inside it will fuse elements, and in the outside the hydrogen will stay all the same. However, if I have a rapidly rotating star like this, then the material from the outer layers is likely to be processed inwards into the core and vice versa. That means that the core is constantly refueled and can fuse more elements. and the outside of the star gets enriched with heavier elements. And these rapidly rotating stars, the second interesting point about them is that they have very strong stellar winds. So we transport the processed material to the outside of the star, and then we expel it via stellar winds into the intracluster medium. On a similar line, we have the idea of interacting binaries. So we know that most, if not all, stars form in binaries. And inside of a cluster, we will have a lot of them. And what can happen if you have a binary star is that these two stars in the binary get so close to one another that they start exchanging material. So what you would have in this picture is a donor star here and an accretor star here, and material is sucked away from the donor star onto the accretor star. Now what happens in such a scenario is that the accretor star here will spin up as it eats material. It will spin more and more and more rapidly. And that means that now, of course, first of all, we have a way to producing another rapidly rotating star. But the other thing is that at some point, this star will actually rotate so rapidly that it cannot accrete more material. But the material is still sucked away from this donor star. And what happens then is that this material is ejected into space. So we have another way of injecting some more massive elements into our molecular clouds. And the last and maybe most straightforward hypothesis I want to talk about is that, well, stars might just collide. And if they collide and merge, what can happen is that a lot of debris is ejected into space. Now, we don't know which of these scenarios or which group of these scenarios actually causes what we see on the sky. This is still one of the open mysteries in science. But I hope that in the following years or maybe decades, we will get behind this. Now with that, thank you for your attention, and I want to leave you with my favorite stellar cluster on the sky. This goes by the very memorizable name NGC 3603YC. And this is a very young stellar cluster. It's about 4 mega years old. And you can still see here on the bottom of the picture and here the remainders of the gas cloud this cluster once formed out of.